I'm Camilla Thomson. I'm a postdoctoral researcher at the Institute for Energy Systems, and my research focuses on looking at the carbon footprint of power generation and also the impact of renewable generation on the national grid. So I'm kind of linked to what Brian did earlier in the same institute in that I'm interested in carbon, but I'm looking at it from a much more electrical side. So I'm going to talk to you today about this question. These are some headlines that appear in the press every few years, and what I've generally found is that, in fact, all three of these were based on quite poor quality research that has unfortunately been reasonably influential. So what I'm going to present to you today is my research, which has essentially come to this conclusion, that large-scale wind farms connected to the national grid in Great Britain do reduce carbon emissions. Now, I have lots of blank slides, at least two. So one of the first arguments that come up when people look at wind power and carbon emissions or argue against it is that there are greenhouse gas emissions that associated with the wind farm itself. It's actually responsible for emitting carbon or greenhouse gases. I use the terms interchangeably. And this is true. The image on the left is a concrete foundation. The image on the right is a steel foundry. Both of these both concrete and steel have quite significant carbon footprints, and they're both used in constructing wind farms. This is another article. What this article doesn't mention until quite far down is that it's actually quite a good piece of scientific research based on building wind farms on peat bogs, which is a particular issue in Scotland, where it's currently estimated that between 30 and 55% of planned and existing onshore wind farms are built on peat. And the problem is that when peat is flooded, it actually absorbs greenhouse gases. And when you drain it, it releases those to the atmosphere. When you build a wind farm, you take some of the peat out to build the foundations. Around the foundations and around the roads, you actually drain the peat. That dries it out and it increases carbon emissions. And this is a real problem that the Scottish Government is aware of, and it's actually them who are funding the research into this. So what do we do about that? Well, there has been quite a lot of research into the impacts of wind farms on their life cycle greenhouse gas emissions of wind farms. Back in 2012, the National Renewable Energy Laboratory in the USA did a really comprehensive review of existing work in this area, and they identified 50 pretty robust studies on this, and there have been quite a few published since then. And what they found, these are the results that they found for onshore wind. You can see there's quite a range in the results there. I've given you the range as they publish it, and this is because there's lots of different variations when you're building a wind farm of different technologies, and so we make different assumptions, and that's why there is a range there. The average is about 11 grams of carbon per kilowatt hour, and I'll talk about what that means in a minute. For offshore wind, the range is smaller, and that's simply because fewer studies have been done. So offshore wind is more of an emerging technology, it's more of an emerging area, and we expect these numbers to become more robust over time. NREL didn't include any of the studies on the impacts of construction on peat, so I've included building an onshore wind farm on peat there. So this is from very few studies, a handful of studies that have been carried out, and you can see the range there is 60 to 100 grams of carbon per kilowatt hour. What does that mean? We've got to set it in context. So two other large forms of low carbon generation on the national grid are hydropower and nuclear power, and the current estimates are sitting way down under 10 grams of carbon per kilowatt hour. However, there are problems with these values. We know that the hydro studies rarely include the impacts associated with flooding the reservoir. When you flood the reservoir, when you first build your dam and flood your reservoir, you inundate the vegetation, it gets covered in water, it starts to rot, and it releases methane. Methane is has a very high global warming potential. It's about 20 to 25 grams of carbon per kilowatt hour per gram of grams of carbon per gram of methane. Nuclear power, none of these figures actually include waste disposal or decommissioning of nuclear power stations. So you've got to try and include that as well. But anyway, so you can see wind isn't our estimates for wind aren't that great when we compare them to other low carbon generation. But when we compare them to the two other main forms of generation on the national grid, combined cycle gas turbines and coal-fired power stations, they're minimal. Well, that seems like great news. But it's only great news if wind power, when it's operating on the grid, is replacing these fossil fuel types of generation. So this is what happens on the national grid. Unfortunately, the left-hand edge is cut off. Sorry, right-hand edge is cut off, but that says generation in gigawatts. This is data from the 9th of December 2012. So it's a typical winter's day in 2012. And it shows how the grid is operating. So that's the yellow line there represents the wind. You can see that the wind generation is changing over the course of the day. It was quite low in the middle of the night, and then it increased. Nuclear power is at the bottom. Nuclear power doesn't, in the UK, this is on the British grid, nuclear power doesn't change its output really at all, except if it needs to shut down in order to have maintenance. At this time, coal-fired generation wasn't changing that much. It was actually it was responding slightly to changes in demand, and the main one that was changing was your combined cycle gas turbines. There are other forms of generation on the grid, and they are represented by those other lines, but these are the main ones. But the problem is, we can see that the output from all of these is changing, but what is wind actually replacing? Well, it's not replacing nuclear, because the nuclear is not changing in response to anything. But we can also see that the demand is changing over the course of the day, and other types of generation are having to respond to that. Furthermore, there is an argument by several people that coal-fired power generation can only ramp quite slowly. It can only change its output quite slowly. So how is it supposed to respond to changes in wind power? National Grid say that wind power is displacing a mixture of coal and gas, but they don't know how much. They don't know what ratio of the two. And the other problem that they have is that they also don't know the impact that wind power has on the efficiency of fossil fuel generators. So in order for generators like CCGT to respond to wind power, it will actually be operating at part load. A lot of the reserve capacity is to start operating these power stations more and more at part load. And the problem with operating them at part load is that they operate at a lower efficiency. This means that if you take, let's say, Drax power station, it has generators that are rated at a bit over 600 megawatts. If you take only 300 megawatts from one of those generators, you're not going to save 300 megawatts worth of carbon emissions. You're actually going to save a bit less than that because your power station is going to operate at a lower efficiency. So these are things that are potentially bad news, and until my research, nobody had really looked into them. So what I did was I took real data from the national grid. It's a combination of metered data and market data that's been published since the end of 2008. And I looked at 6 years of half-hourly data, which is over 100,000 data points. And I calculated I looked at the change in demand and the change in wind power over those half hours, and then calculated the change in greenhouse gas emissions, taking into account the inefficiency of a power station that's operating at part load, and was able to extract from that the change. I used multiple linear regression. I should probably put some maths into this, in order to extract from that the change in greenhouse gas emissions that you can actually identify as being attributable to changes in wind power output. So this is over very short time periods. And I did this and ran this analysis for each year. So these are my results. Again, I have confidence intervals, but essentially the line in the middle is the likely result, and these are your 95% confidence intervals, and this is what I found for each year of my data set. I haven't run the data for 2015 because it was only published last month. So what's interesting about this? Well, what does this mean? First of all, you can see that the values on the left-hand bar are considerably higher than 11 grams of carbon per kilowatt hour, which is good news for wind. The second thing is people say that wind power can't replace coal, but if it's only replacing gas, how is it higher? How is this emissions displacement higher than the average carbon emissions associated with gas-fired generation? The only two types of generation on the national grid that are higher than this sort of 600 grams value is oil-fired generation and CCGT, and oil-fired generation is negligible. So it must be replacing some coal, and coal has almost twice the carbon emissions of gas. Secondly, why is it falling over time? Well, I can tell you why the confidence interval is getting better over time, and these bars are getting smaller, is because we're getting more wind on the network, so my results are, it's clearer how the network is changing in response to wind because the changes are bigger. But it's falling as well. And I've looked into this, and this drop is actually because over this data set, from 2009 to 2014, the price of coal and gas changed. In 2009, we were actually operating gas in preference to coal, and therefore it was better for wind power to displace more coal-fired generation, which was the more expensive type of generation at the time. And so it was saving more carbon. Unfortunately, since then, the price of gas has gone up and the price of coal has fallen, and so we're now operating the grid the other way around. We're actually operating more coal, and the wind is replacing more and more gas. Now, wind always has to replace some gas. Well, what does it mean for how good wind farms are? Well, we've always assumed that wind farms replace the average emissions of the grid, and we know that's not true because if the average emissions are affected by that nuclear power, which we know isn't responding. But these are the published average emissions. The average emissions factor is published by DEC every year over this time period. And we can see that from 2009 to 2013, the estimates for how much carbon was saved by wind farms were actually pessimistic, which is actually good news for a wind farm. So it says that if we're saying that wind farms are going to pay, a planned wind farm is going to pay back in a couple of years or in 6 months, which is typical value, we were actually being slightly pessimistic, and it was paying back a bit faster. In 2014, we have a little bit of a problem because this value is higher than the value that I've calculated, but it's really similar. So that's quite good news. The next thing is, I suppose, to try and put this in context. I ran these numbers on Monday. This is the installed capacity of wind operating according to Renewable UK on Monday of this week. It's 13.6 gigawatts throughout the UK, although my values for carbon savings are only for Great Britain. Looking at those studies I mentioned earlier, and assuming that 40% of all onshore wind farms are built on peat, which is unlikely to be true. That's likely to be quite a pessimistic estimate because England has a lot less peat than Scotland, and I have no idea what's happening in Wales. So if we assume that, the worst case, we've got 24 megatons of carbon dioxide have been and will be emitted over the full life cycle of these wind farms. My data set is for 6 years. Over that time, I know, because it was metered, that wind power generated 69 terawatt hours of energy. And because I've estimated the emission savings of that, this equates to an emission saving of 36 megatons of CO2. It's a really simple calculation. You can see we've saved about 12 megatons of CO2. Now, people who talk about carbon dioxide will say that 12 megatons of CO2 is not very much for a whole country, and it isn't. But the important point here is that the lifetime emissions were more than fully displaced in 6 years. And these wind farms that I'm talking about have a 20-year design life. So they've still got at least 14 years. Some of them might have only been completed last week. They've got at least 14 more years to operate. And over that time, they will only be saving emissions. So I think this is my conclusion. But the one thing is that moving forwards, we do need to consider the operation of the network with regards to saving wind. But in terms of wind farms, they are good, and they are reducing carbon. Thanks.
This production is brought to you by the University of Edinburgh.